In the previous video, I worked out the classical case of a particle like an electron processing around a magnetic field, trying to line up the magnetic moment with the direction of the magnetic field. And we had this classical result of the precession frequency is equal to the gyromagnetic ratio, gamma, times the magnetic field, where that gyromagnetic ratio, gamma, is equal to the magnetic moment divided by the angular momentum. So the angular momentum of the electron rotating around the magnetic field that is trying to line up with. So now, since we're looking at angular momentum, let's try and derive this not classically, but quantum mechanically. So what is the quantum mechanical way of trying to calculate this result, say this precession frequency or the gyromagnetic ratio? So we're going to start with angular momentum. Actually, we're going to start with orbital angular momentum. So what we have is a charged particle of mass m. So Q is the charge, m is the mass of this particle that we have inside a magnetic field B. So what we want to do to get the quantum mechanical result is to first write down the classical Hamiltonian and then convert that Hamiltonian into operator form to get the quantum mechanical Hamiltonian. So the Hamiltonian for the charged particle in a magnetic field is the momentum, the linear momentum, minus the charge divided by c times this potential. It's a vector potential, actually, squared divided by 2 times the mass. So if we write this out, what we get is the momentum squared over divided by 2 times the mass. So that's the kinetic energy minus Q over 2mc, which looks familiar. That'll be related to the gyromagnetic ratio times momentum dotted into the vector potential plus the vector potential dotted into the momentum. So we're going to make these into operators, so we have to be careful about the order of operation. So instead of calling it 2 times p dot a, we're going to keep both possibilities. Plus, the last term is q squared over q squared a squared over 2mc squared. Okay, so let's come up with a good form for this vector potential. So the vector potential A, let's say it is the magnitude of the magnetic field divided by 2 times minus y in the x direction plus x in the y direction. Okay, so now let's look at the cross product, or the curl of the vector potential. So that would be I, J, K, and then the derivative in the x direction, derivative in the y direction, derivative in the z direction, and then ax, ay, az. So if you work that out, what you get is the x direction, the y direction, the z direction, the derivatives, and then you get minus y, x, 0. So if we work that out, then we get in the I direction, we would have the derivative of y times 0, that's 0, minus the derivative of x in the z direction, minus in the y direction the derivative of y in the z direction, plus in the z direction the derivative of x with respect to x, minus a minus, that's plus, derivative of y with respect to y. Okay, so the derivative of x with respect to z is 0. This one is 0. This one is 1 plus 1. So I get k, 1 plus 1, or 2 in the z direction. And what I actually left out of this derivation was the 1/2 b. So really, the what you should really get is the curl of A is 1/2 b times 2 times the unit vector in the z direction. So I should get B, the magnetic field pointing in the z direction. So this A is a good choice of a form because it gives us the magnetic field in the z direction. Okay, so one other thing we're going to do is we're going to assume that if B is small, then this term here, q squared times a squared 2mc squared, is going to go to 0. So we're going to neglect that term as just insignificant. Okay, so now let's take our vector potential and let's consider these operators. So P dot A operating on some state psi is going to be I minus I h bar the derivative dot A, like so, operating on psi, which is now minus I h bar the derivative of A, that whole thing operating on psi, plus the A and basically the chain rule of the derivative operating on psi. So if we look at this, what is del dot A? Well, that's going to be the derivative of the x direction of A with respect to x plus the derivative of AY with respect to y plus the derivative of AZ with respect to z. And if we put all this in, I get minus the derivative of y with respect to x plus dx dy plus 0 is equal to times the magnetic field divided by 2, and that is going to be equal to 0. So that term right there of del dot A is going to be equal to 0. So that means what's left of P dot A operating on psi is minus I h bar A dot the derivative operating on psi, which is A dot minus I h bar del operating on psi, which is A dot P operating on psi. So we initially broke it up into two operators because we weren't sure how these the P dot A and A dot P were going to act. but it turns out that they're exactly the same. Basically, it commutes. And so now we can write our Hamiltonian as minus q over 2mc 2a dot p. That's our operator, which we can write out as b over 2 times 2 times minus y px plus x py, which is the angular momentum operator. So the 2's cancel away at minus q over 2mc b times L, the angular momentum operator. In this case, it's actually in the z direction, but we could expand this into all three dimensions by writing down minus q over 2mc L dotted into b. Now if you remember, the magnetic moment is q over 2mc times L. So that means, even in quantum mechanics, the interaction Hamiltonian, basically the potential energy, is minus the magnetic moment dotted into the magnetic field. So even if we work it out with quantum mechanical operators, we still get the same function of the magnetic moment times the or magnetic moment dotted into the magnetic field. So if we only look at the z direction, then what we get is the magnetic moment in the z direction is q over 2mc times the angular momentum in the z direction, which means that our quantum mechanical operator for the magnetic moment, operating on some state of angular momentum L with a projection m, is q over 2mc Lz operating on that state. And when we operate on that state, we get an eigenvalue of I'm going to write this now as m sub L, to differentiate it from the mass, times h bar, the state Lm back again. So in the end, we can now group our terms, and we have q h bar over 2mc times the magnetic quantum number times the state Lm. So if we group these terms, we can call that the Bohr magneton. Which works out to be, for an electron, we have q h bar over 2 mass electron the speed of light, which what you get out of that is 0.6 times 10 to the minus 8 electron volts per Gauss. So that's how much energy there is in the magnetic field in this particular unit, and then you can multiply it by whether it m equals 1 state, m equals 2 state, so forth and so on. For a nucleon, like a proton or a neutron, what you get is a Bohr magneton of 0.3 times 10 to the minus 11 eV over g.